Alright, so light has physical properties, it has geometric properties. We are going to spend a good deal of time actually dealing with those properties, but of interest at the moment is how we interact with them. Primarily, that would be through cameras, and although there are a lot of regular film cameras in the photogrammetric industry, probably the vast majority of cameras still are film cameras, most of those images end up being scanned as digital images, or there are a lot of photos that are directly imaged by digital cameras. So we want to understand digital images. First thing that we want to understand is you'll hear the term raster file. Digital images are raster files. That word basically means that they are organized in rows and columns. You can almost think of it like a spreadsheet. A spreadsheet is in rows and columns. Each cell has an address. It also has a value. In the same way, every row, column, address in a digital image has a value. In this case, there's some sort of color assigned to it. Raster files don't always mean photographs. They're usually imaged, they're usually viewed as some kind of an image, but each of those addresses could just as easily have an elevation in it rather than a color. In that case, it would be known as a digital elevation model, or DEM, where every row, column, address has an elevation. Most image formats call the upper left hand corner 0, 0. As they increase in Y, they go down. As they increase in X, they go to the right. Don't ask me why. I have no idea. Probably has something to do with the monitor and how things were painted on the monitor. And everything would have been a lot easier if they had just said the lower left-hand corner was 0, but it's not. The upper left-hand corner is 0. X increases right, Y increases down. We also need to understand that those addresses can have a variety of data in them. We would call that color depth. It's usually expressed in how many bits of data each address holds. The upper left-hand corner, the black and white image, 8 bits of data, 256 colors, everything from 0 being black to 255 being pure white, and everything in between, 8-bit black and white. To the right, upper right-hand corner, we've got a 1-bit image, only 2 possibilities per color, black or white. Come down to the lower right, we've got an 8-bit image again. However, instead of being black and white, each of the 255 colors is drawn from a palette. There are 255 possible colors that can go into each one of those addresses. And then the lower left, what we would call true color, or as true as you're going to get in most image formats, 24-bit color depth, 16 million some possible colors. Well, how does that work? Why is it like that? If we start with the simplest, the binary image, you can see that each one of those addresses only has 2 possibilities. 1 bit, we're not talking bytes here, 1 bit, 1 binary switch, 0 black off, 1 white on. So everything has to fit into those 2 possibilities. With an 8-bit pixel, now we have each of the pixels has, each of the bits have a possibility, 0 or 1. That gives me 256 different possibilities. I can either assign that to black and white or throw a color on each one of those numbers. The term RGB, true color, 24-bit, all mean basically the same thing. There are 3 color planes, red, green, and blue. Each one of those has 0 to 255 different possibilities. So that gives us 256 to the third power, or 16 million possible combinations. If you're working with a paletted image, the math there is that if I am willing to allot, let's say, 4 bits of memory to each color, that's going to give me 2 to the fourth power. Okay, D is the depth, 2 to the D power different possibilities. So you can see binary, 2 to the first power is 2. 8-bit, 2 to the 8th power is 256. Well, maybe we don't need that. Maybe we're working with something like a digital raster graph or a DRG quad file. Here they only use a 4-bit palette because they don't need that many colors. I mean, these were created with probably no more than 8 different color plates. So they use a 4-bit palette, 2 to the fourth power, 16 possible colors. Just to belabor the point, why is 4-bit color, 4 possible combinations, why does that give me 16 different values? Well, if you look at the bits, how the switches are set, what I've done here is put up every possible combination that you can get from a 4-bit combination of switches. You can see there's only 16 different possibilities, whether it's black and white or a color, 0, everything off, all ones, everything on, 16 different possibilities. You need to understand the idea of file size is crucial in delivering images. Understand that if you double the dimensions, we're going to increase the file size 4 times. So file size is geometrically proportional to the scale factor. Scale factor by 2, increase file size by 8. Scale factor by 4, file size by 16. Why? Well, you can see if we've only got 4 by 6 pixels, we only have 24 pixels. But if we double the 4, that's also going to double the 6 to 8 by 12. Now we've got 96 pixels. It increases in both directions. The bit depth, whether it's 1-bit, 8-bit, or 24-bit, right? A byte is 8-bit, and I mention that because typically we talk of things like kilobytes, megabytes, gigabytes. So what we have to understand here is that when we're doing a conversion, if we've got the bit depth, we're always going to need to divide by 8. So the file size is the width in number of pixels times the height in number of pixels times the bit depth. If it was true color, the bit depth would be 24, and then that would be divided by 8 to switch it to bytes. And what we'd have then is our file size. So if I had an image that's 2,000 pixels wide, 1,000 pixels high, 2,000 times 1,000 times, is it an 8-bit? Is it a 24-bit? Okay, 2,000 times 1,000 times, let's say, 24 divided by 8, and that's going to give me the number of bytes. Once we do that, then we usually express it, divide it by 1,000, actually 1024, but usually we're going to divide by 1,000 and round it off to get kilobytes, divided by 1,000,000 to get megabytes. or by 1,000 million, which would give us gigabytes. So file sizes, understand file sizes and why they get so big so fast when we're talking about large images at high bit depths. The last thing to understand here is the concept of dots per inch. It's the same as pixels per inch. It's going to be the same in both directions. We work with square pixels, so something that has a certain DPI in one direction is going to have the same DPI in the other direction, in X and Y. DPI doesn't mean anything until you display the image, particularly until you print the image. Okay, I can have, we'll go back to that image that is 2,000 pixels wide. Now internally there may be a tag that says that image was scanned at 1,000 DPI. So we've got this 2,000 pixel wide image and the file says it's a 2,000 DPI image. If I print that 20 inches wide, then 20 inches divided into 2,000 pixels, okay, pixels per inch, it's only going to be 100 DPI. It's not going to be a 1,000 DPI image if I plot it at 20 inches. You know, the example on the screen, 1,000 pixels, 10 inches, it is 100 DPI. The effective pixels per inch is 100. Typically, we're going to shoot for, if we're plotting something, we're going to shoot for about 200 DPI because we found that your eye really can't see anything better than that. I mean, we can scan it, we can process it, we can make it so that I could print it at 600 DPI, and I'd be completely wasting all that file size if the end product is a print. Now, the higher resolution is going to help when I view it on the screen and zoom in on it. But if the purpose of it is a print, if I'm going to take my digital image and send it to Sam's Club and have it printed on a 4x6 piece of paper, then having 10,000 pixels is a complete waste because my eye can't see it anyway. Generally looking for about 200 to 300 DPI when printed, if that's the final product. Aspect ratio, we'll talk about that a lot. You need to understand just the idea of the ratio of the width to the height. A common screen resolution is 1024 or is 1280 by 1024. An aspect ratio of 5 to 4, or reduced to the most common terms would be 1.25 to 1. When I'm scaling images, changing the size, typically there's a little checkbox that says maintain aspect ratio. If I make it twice as wide, do I want to make it twice as high? Yes, unless I want to distort it in some way. There's a lot to talk about in the area of digital images. We'll spend whole sessions on changing and modifying and manipulating digital images, but for now, that's the basics that we need to know.